We will start with the convolutional neural networks. The convolutional neural networks are the type of deep learning models that are universally used for the computer vision task. Okay. Basically, it is the advanced version of the artificial neural networks, that is feed-forward neural network, or multiple MLP, right? Multi-layer perceptrons. And in recent years, the convolutional neural networks, or they are in short form, they are also known as CNN or ConvNets. They have achieved some superhuman performance in different complex visual tasks, visual recognition tasks. Then they are applied on different type of computer vision problems like image classification, object detection, image segmentation, and many more. And not only these computer vision tasks, they are also being applied in different type of problems like voice recognition, then natural language processing, recommender systems, and the time series analysis. Now, our problem is to identify or to classify an image. There are handwritten numbers, suppose this. So as we can see that it is a 9. But the computer doesn't understand what it is. It is generally a set of pixels or a matrix of pixels, right? And just a second. Yeah, and wherever the important features or important pixels are there, they are having some values, like the structure of 9 having whichever pixels are overlapping, they are having some values, right? And others are 0. So this is not a generalized case. Just for an example, I am showing this one. Okay, but in actual there might be some different numbers. Okay. Now to highlight these pixels, like the computer sees the image like this one. Okay, so computer identifies this one as a 9. But how to train that machine that this is 9? Right? There may be some other cases too. Suppose the 9 in the image is shifted towards left side, like this one here. Okay. So the pattern is same, but the arrangement of the pixels, those are representing this number 9, is showing different different positions. They are in different positions, right? And suppose someone write the 9 in different font, like this one, right? So again, it will have some different representation. Right? But in that case, in previous, the 9 was here, so the computer will get confused that whether it is a 9, or the machine will confuse that whether it is a 9 or it is a 9. So it is different from this one. Okay. So there may be n number of representation of a single object, like I have shown here, that 9 can be written in different type of fonts. So there may be variation in the data set of a same object, of a same type of image. There may be variation. So to handle that variation in the data set, the concept of artificial neural networks come, or the MLPs. Now let us see how MLP or the ANNs will deal with this. Okay. So this is an image of 9. Now the computer will read this one, the array of or the matrix of a pixel having this arrangement. Okay. Suppose it is a 7 by 7 image, and the total number of pixels in that image is 49. Right. Now, what the ANN will read, as we know that ANN having an input layer, then there is some hidden layers. Yeah. And then there is the output layer. So, and the input, the layers are constituted with different nodes or neurons, right? So in this case, whenever we are using artificial neural networks or the MLPs, the pixels are the neurons here, right? So we have to make it as a vector because ANNs can't process a vector matrices, or matrices they can't process them. They have to read input in a one-dimensional vector, right? So we have to convert it into a one-dimensional vector, right? So each pixel will be one image, one input node here. Okay, so this becomes the first layer of the neural network here. All the 49 units are representing the first layer, and they will having some weights. All are having some weights, W1, W2, Wn, and they are connected to the output layer, or maybe some hidden layers also there between them. Okay, and after that, those hidden layers will generate the output like this, the final classification layer. Okay, and in the final layer, we will have some probability values representing that. Suppose as it was 9, so the output will be representing that the this neuron having a 91% that it is 9, and it also tells that it is 0.5 value having it is 4, right, or 5%, like this. Okay, so this is the case for artificial neural networks. Now, so this was a small image having only 7 by 7 pixels, that 49 pixels. But in real case scenario, suppose this image, its size is 1920 by 1080. Okay, just a second. Huh? Yeah. So in real case, the images are of almost like this size, right? So there may be there are around 6 million pixels in this image, and here one thing is there, that is 3 is for as we know that images are represented by RGB, so each one is considered as one channel, right? So in each channel there are this number of pixels. So in 3 channel, if it is a color image, then there will be this one into 3. So if it is a black and white image, then this one will be, this is 1. Right. So the number of pixels now, it is 6 million. Okay. So in the previous slide, as I show that the input layer of the neural network, it will have all the pixels in its first layer, right? So the input layer of the ANN will have 6 million neurons. Now suppose there is one hidden layer, right? And suppose we reduce it to half, and we say let there are 3 million neurons or 3 million nodes. So now for a single hidden layer, we will have 6 into 3, that is 18 million weights, or 18 million interactions between the input and the hidden. As we know that in ANN or MLPs, all the neurons are connected to the next layer, that is the hidden layer, right? So is this too much computation, right? So for any computer, whether it is having high computing processing power, it is very difficult to compute this or process this image. And this is for only one image, right? But whenever we are training some or we are doing the problem of image classification, we are having minimum of like 200 images or 300 images, or even we are having 2000 images also. So for that case, this will again rise to some huge number. So the computation will be huge, and that is not possible for any computer, any high performing computer also, to perform such computations. So what is the way around? So in that case, that convolutional neural networks comes in the picture, right? They are having some different type of layers. They apply those layers, and after that they classify the images. Now let us go around with the convolutional neural networks. Okay. Before going into details of convolutional neural networks, let us see how the CNNs are emerged in the real life picture. Right. We all know about the visual cortex, biological visual cortex, whether it is a human, whether it is an animal. Right? So in visual cortex, there are there are neurons present there, right? And those neurons are activated based upon whatever the scene we are seeing, and if there are some changes on that scene, those neurons will be activated and they will process further, and ultimately we see the images and we learn the images. Right? Okay. So these experiments were done during 1958-1959 by Hubel and Wiesel, and their experimental results report that there are some neurons having small local receptive fields, and some neurons having large receptive fields. So what is this thing? Suppose we are seeing this whole image. Okay. In this image, some of the neurons will see this part, these small parts, right? And it will learn these patterns, small patterns, whether it is a line, whether it is a curve, right? And it will pass this information to the next layer. And next set of neurons, what will they do? They will capture or gather information from previous layers and combine them and again learn some combined features, right? Like this one or this one. Okay, and this way, learning the representations from lower level to higher level, they are ultimately learning the whole image here, right? So this was the case for biological visual cortex. This same thing happens with humans and as well as different type of animals, right? That's how we learn things, that this is a house, this is a cat, this is a dog, right? So this biological the concept of this biological visual context, that has been implemented in the convolutional neural networks. Okay, from that, the development of neocognitron was proposed during 1980s, and after that, the first convolutional neural network was applied in classifying or recognizing the means images that were handwritten digits of bank checks in 1998. So this was the first breakthrough, or you can say this was the first convolutional neural network that was applied for that image classification and shown significant results. Okay. Now, what is happening in this case? Suppose this is an image of silver bird. Okay, the original image. Whenever we pass it to that convolutional neural network, it will read the image. First, what it will do? It will check that whether this part is the silver bird's beak, like this, right? Now it will check that whether the eye, this portion represents the eye of silver bird, okay, and these portions representing the crown, yes, and the wings, and the legs and the tail. Like this, these are the lower level features they will identify first. Now they will combine these lower level features and they will learn some higher level features. As we know, as I told, that some neurons having some higher level receptive fields, right? So they can capture some higher level information from the images, right? So by combining these small features or the low level features, the next level of neurons, they will learn that this is the head portion of that image or this bird, and same the body portion of that image, right? So this is only for the understanding. There may be some n number of means low level features and high level features will be there in actual processing, but those things can't be represented in this graphically here. Okay, I'm just telling for the understanding of this lecture. Okay, and finally these features will combine and say whether it is a silver bird or not. So if these features matches, so the network will tell, yeah, this is silver bird. Okay, and if these features doesn't match, then it will tell, no, it is not silver bird, or some other bird will be there. Okay, so again, it will be same for the numbers or any type of images. So this type of edges, that upper portion is curved. In this case, the left portion is curved. Here, the lower portion is curved, and this will contribute, right? This will contribute to some bigger pattern, that is loopy circle pattern, right? And lower level features having some straight lines, straight line type, right? Vertical line, and there will be some diagonal line, and ultimately it will tell that this is a number 9. This is the way the convolutional neural networks work, that it will learn the lower level features and means in consecutive layers or sequential layers, the lower level features merged to some higher level features, and like this it will learn. So how this actual thing is happening here, what is the mathematics there, what is the concept there, right? So in any CNN or convolutional neural networks, there are mainly two modules. That one is feature extraction module, right? And another one is the classifier module. So the feature extraction module is the feature extraction module is consist of the convolution operation and pooling operation. Right? There are two operations are there, convolution and pooling. And in the classifier layer, it actually classifies whatever the features we have extracted into the respective classes. And it simply resembles the structure of the ANN, where all the input nodes are connected to the output nodes. Right. So we will see in the next few slides. Right. So now let us talk about the convolution operation. It is the most important or the most basic building block of the CNN. Okay. Here, as we already told previously, that in case of CNN, in case of ANN or the MLPs, all the nodes of one layer is connected to the nodes of the next layer. But this is not the case for convolution layer, right? So whenever we are applying a convolution layer in any layer, convolution operation in any layer, so it becomes a convolution layer or conv layer. Okay. So here, what is happening? Suppose we are applying a convolution operation in this portion, right? So the neurons of this portion, and it will generate some other next layer. In the next layer, so these neurons are connected only to these neurons. So this neuron will not connected to this neuron, right? So this will not happen. Okay. So this is the case. That means that each neuron is not connected to each of the neuron in the next layer or the previous layer. So that's how the connection or interaction between input and the next layer is reduced, right? So what is the basis of this convolution operation? It is a mathematical operation simply denoted by this symbol, asterisk symbol. Okay, and it generates. It is an operation on two functions that tells that the output of this operation shows if one of the function if the function shape of that function is changes, and then how the shape of that other function will change, or how the shape of the other function will be modified, right? So this is the basis of the convolution operation. But in case of the 2D image, because it is a digital image, so all the variables or all the values are in discrete discrete values. So the equation will be reduced to this one. Okay. So this is the output image. We are applying some operation and we are getting some output image. And this is the function here, applying k and I for a particular pixel position ij, and a double summation because the we are having k is a kernel. Okay, I will tell what is kernel here. A kernel of size m by n, and the summation of the dot product, right? So ultimately, convolution, what convolution is doing, it is doing the sum of products between two functions, right? So here I is the input image, k is the kernel, and the s is the output image, that is the feature map. So let us take this example. Suppose this is one image, this one original image I, okay, and we are applying some other function that is k of size m by n. Okay. So we are applying some kernel here, and ultimately the dot product is happening between the kernel and the image for that particular position in that image, and it will generating a output image or output feature map. Okay, so suppose this is a kernel, and this is the this one is the image, and each kernel having some values among themselves, right? And the corresponding values of the kernels are multiplied by the corresponding values of the image, and their sum of products will be represented in each position in the output image. Okay. So there were two terms in that equation. That one is kernel, that was represented by k. It is simply the set of weights, right? In ANN, as we know that each input node having some weight, we apply some weight on the inputs, and based on that input, the output is calculated. So in case of convolution also, we apply kernels. Okay, kernels are two-dimensional matrices. They are representing the weights for the input layer, right? Or input, whatever the input image we got. Okay, so and the size of the kernel is determined by the size of the local receptive field of the input, right? So if we are interested on to have a receptive field of 3, so we will define a kernel of 3 by 3, and we can have of 5 by 5 or 7 by 7. And so the weight matrices or the kernel will have a set of values, right? but we don't know what the values will be there. In case of CNN, the weights will automatically at the first it will randomly initialized, and it will automatically update it with an optimized value, so that the input image will have a better representation, or the model will learn the features from that image. And the feature map, it is also known as the activation, that the output of the convolution operation, it generally represents the set of linear function feature activations. Right? Whenever we are applying the that kernel to a specific location of the image, it will activate the features that are important for the particular feature, right, or the for a particular pattern. So what is happening in the convolution? It is extracting the feature by convolving a set of filters through the image pixels and generating a set of feature maps. So let us see. So this is the image that we encountered earlier. So it is representing the 9 here, right? Like this one. Okay. So suppose we have defined one filter, but in case of CNN, in actual case, there are n number of filters we have to define, right? Because for one filter we will get one type of pattern, right? So if we define more number of features, so then we will get the different type of patterns that can be learned by the model. Okay. So in this case, as I told, the sum of products will happen, and the result will be stored in some the output image. Kernel is 3 by 3, and the input image is 7 by 7. Right. So we are performing the dot product between the elements of the kernel and the elements of the image for the particular receptive field, right? So at first our receptive field is this position. So the dot product will happen here. This multiplied by this plus this multiplied by this, like this, it will happen. Okay, and the sum will be the output in this case. Now we are at the first position. Okay, from this is our kernel, and if we are talking about this position of the image, so the having the sum of means some dot product is happening, and this sum is represented in this output here. Okay, now what will happen? We will slide this. Let me remove, then you can understand here. Yeah. Now you can see in the next step, the kernel is, or the receptive field in the image is shifted one position to the right. Okay. Now what we will do? We will take these elements. Now the kernel will process these elements here, and again the sum of product will generate this output, and like this the whole image will be read, or whole image will be processed like this. And again, after one row has finished, then one row below the previous one, like this, the whole image will be read, and this output image, or the feature, we ultimately say it is a feature map or activation map for this input image, will be generated. Okay, so now this feature map, the size of the feature map having a relation between the input image and the kernel, right? So this is the formula here. The I is the input image, size of the input image, that is 7 here, and F is the size of the kernel, that is 3, and there is two terms here, that is P and S. So P means here, that is padding. Okay. In some cases, as we can see here, whenever we are generating this feature map here from the input image, the size is reduced. It is 5 by 5. Okay, that means we can say that some information is lost, but actually it is not happening. The information is not lost. But for the sake of this lecture, we will say that some information is getting lost here. So what we will do to maintain this feature map as 7 by 7, we will add some additional rows here and additional columns to each side of the image, and these rows or columns having 0 values only. So this thing is the padding concept, right? So you can add two rows or two columns in each side of the image with 0 values. So this is the padding here. Okay. So now you get my point. So in this case, our we didn't apply any padding here. So this is 0. Okay. And second term is stride. Striding means that how much position or how much pixels we are shifting during the process, right? So in this case, we were shifting one position, right, like this. Okay, whenever we are processing the sum of products we are generating, we are shifting one position at a time, right, or one pixel at a time. So s is equal to 1, right? So this padding p and s, it can be different. You can having a padding of 2 zeros in each side. You can having padding of 1 zeros in each side. You can having a stride of 1. That means you are shifting one position at a time. You can have a stride of 2. That is, you are shifting 2 positions at a time. Okay, and ultimately this all these variables will determine the size of the feature map. Okay.
The padding. What is the padding, sir? I'm not.
Oh, sir, as I told earlier that here the input image is 7 by 7 and our output feature map is 5 by 5. Right? So to maintain the image size in the outputs, we can add some additional rows or columns in each side of the image, each side of this pixel or the matrix, so that the output image will have some same dimension as the input image, and the additional rows will have 0 values only. They will have zeros. Like here, I am adding one row in the upper side. Likewise, if we have to add in all the direction, right? In all direction, we have to add like this one. Okay. So in this image, you can see in original case, the images, the original image is like this one, right? And we are having a padding of 1 0 in each side. Okay. So this is the padding. No. So यहाँ पे 3 channels की बात किया है, that is having red, green and blue. As we know that in color image there are 3 channels, right? And each channel is represented separately by the array means matrix of a pixel or array of pixels. So and for each channel, the kernels will generate feature map separately. Okay, so here जब हम एक input image की बात करें 7 by 7 में ये kernel apply हो रहा है, so it will be applied on the other channels also, right? In this case there are 3 channels, so the kernels will apply on the all 3 channels and ultimately it generates the output here. Okay, like that. So whenever we are applying the convolution operation, we define the number of kernels that suppose 32, 64. In the power of 2, we define the kernels here. Okay, that means we will have we want to learn 32 kernels from that particular layer. if we define the kernel as 32, and it will generate 32 feature maps from the previous layer. Okay. Now, the main characteristics of the convolution operation, that is the sparse connectivity, means, or we can say sparse weight. As in the ANN, as we see, suppose there are 3 layers and there are 3 input hidden layer. So each node is connected to each of the hidden layers, right? So there are total means the weight connectivity, or the connectivity between the input and the hidden layer is more, right? So the parameters that are to be learned in the in this model, it will be increased, and computation complexity also increased. But in case of the convolution, the pixels in the respective receptive field is connected only to the respective kernels, right? So the number of parameters are decreased and the computational complexity decreases. So let us see this image, right? So suppose first this is the ANN, in which all the nodes are connected to all the nodes in the next layer. Okay, suppose for this particular feature X, and suppose from this layer to this layer, this second layer features are generated. So this node is contributed to each node, each feature in the next layer. Okay, but in case of convolution, suppose this feature is only connected to these 3 features in the next layer, right? So ultimately the connections between the layers are decreased. Okay, so the computation complexity decreased. That problem has been solved. That we have seen that there are 18 million weights. So this will drastically reduce the number of parameters or number of weights in the image. Okay. Now there is a concept of shared parameters. Like parameters means the weight that are determining or that are applied to the inputs for generating the outputs, right? So in case of ANN, the input nodes are vector values, right? But in case of the convolution, those are in 2-dimensional matrix, and we call them as kernel. Okay. So here we can see that suppose a particular weight W, suppose W1, is only related to a particular feature, particular node of in case of ANN. In case of ANN, a particular weight is only related to a particular feature in the input layer, right? So this weight doesn't go to these other ones. But in case of the convolution CNN, for a particular kernel K1, suppose, so for based on the K1, we are getting input feature map in the next layer, and the output feature map having these features, and input having these features. So for all cases, K1 is shared, right, for a particular feature map, है ना? तो ये parameter shared हो रहा है, right, for a particular pattern, a same filter or same kernel is used, right? So this has an added advantage for the convolution or the CNNs. Now, another thing is that translation invariance, right, means कि ये जो parameter sharing हो रहा है, means कि एक particular pattern के लिए एक particular that kernel is learned, so that means a particular kernel is means processing the whole image or every input pixel it is processing. So whenever it will get or it will encounter that its own feature or its own pattern, it will activate in the feature map, right? So that is the translation invariance means if the input image is translated or input image is somehow little bit deviated from the previous one, so the convolution operation will look after that. Okay, that means कि अगर किसी particular location पे उसने कोई pattern को learn किया, so it will be able to recognize that particular pattern in any other location on that image, right? So that has makes the CNN efficient in learning the images. The next operation or the next the layer is pooling operation or the pooling layer. Pooling layer is simply a subsampling process. A subsampling process that will drastically reduce the size or the spatial resolution of the input images or input feature maps. Okay, so ultimately that will reduce the computational load, the memory usage, and the number of parameters, right? Again, in this case, there is a specific size of filter is there, right? And the filter is slided over the input image from left to right and to the whole image, and it will typically downsample the input image and generate the output image, right? And by representing the feature map in a smaller images or smaller patterns, this becomes more manageable. Okay. Then in pooling layer, the output of the neurons from the previous layer are connected to a limited number of neurons. Okay. We will see in the next slide what is happening in the pooling. And for each feature map, the pooled feature map is created for every feature map it encounters. So there are two type of feature maps means pooling operation are there generally. That is max pooling, that is applying a max filter, and average pooling, that is applying average filter. So suppose this is one particular feature map that is encountered here. Okay, now we will apply a max pooling feature of a size of 2D filters. Now 2x2 filters. Now, as in the earlier case, we said that the kernels in the convolution having values, but kernels or the filters in the max pooling having no values. Okay, so they are just to define the size of the operation, right? So we are applying here 2x2 kernel in this position, and what we will do, we will check or we will extract the maximum of these 4 values. Okay, so maximum is 32, the output will become here 32. Now again it will be shift to next position. So here 2 s equal to 2, that is tried is to considered as 2 here, because we are shifting 2 position, that is next position will be here. So in this case maximum is extracted like this in this case also, and in this case. So the input feature map was like here 4x4, the output becomes 2x2. So from this it may seem that we are losing some information, but ultimately whenever we apply this operation, the information are not lost, but the spatial resolution is only reduced, but the information is extracted, because whenever we are applying the convolutional kernel on this on this one, on this input, so ultimately the highest valued pixel, highest valued pixel contributes the most on the output feature map. So that is the case here. We are extracting the highest one and representing in some lower representation value. And after that, on that pooled feature map, we are applying some other convolution and pooling layers. Right. So this is the another example here. Right. कि ये हमारा input feature map from the suppose say from first layer convolution, and we are applying pooling here. So here we have taken 2 by 2 kernel. Okay. Suppose the values are here 1, here 5, here 3, here 2. So the maximum value will be extracted in the output, as I told earlier. And so if we after applying the operation, this was the original image, and now this is the pooled image. Okay, so you can see the size, spatial size of the image is reduced, but for the information part of view, right? So the information are intact. The machine will identify, or machine will extract the desired information from that image. Okay. The pooling operation, apart from reducing the size, it will also introduce some level of invariance of small translation. That is the equivariance, or that we said the translation invariance. So the pooling layer also introduce some of the invariances in the translations. Okay. So but the translations should be small, not bigger. Okay. अगर large translation हो रहा है तो that is handled by the convolution operation, but small translation like rotation, scaling, or simple linear transformation, those can be handled. Like suppose this is the original image, so this is the pattern. Okay, now from that image we applied max pooling and we got this one. This is pooled feature map, right, of this A. Now in B, this feature is shifted one position to the left. Okay, but the pooled feature map is having the same as the previous one. Okay, so we can say that small translations are totally handled by the pooling operation. But if there are more translation or larger translation, here 2 positions are shifted. So the it has captured most of the features, but still there are some features are means modified, right? So that's why pooling introduces small level of invariances, right? Only small part. Now we have come to the that second part, that is the classifier. Okay, so the classifier here in case of the CNNs, we call them as fully connected layers, and these layers totally resemble the architecture of the artificial neural networks, all the multi-layer perceptrons, because here all the input nodes are connected to the next node here, or the hidden layers, or the whatever the layer is there. Okay, and sometimes it is also called as dense layer. Okay, so this is the overall view of the convolutional neural network, that we are receiving the image, then we are applying a convolution to convolution layer to extract some feature from this image, and then we will apply pooling that will drastically reduce the spatial resolution of the image while keeping the information without losing any information. And these two, convolution and pooling, can have we can apply many times. Suppose we can apply 3 times, we can apply 5 times, even we can apply 150 times. Okay, after that, what we are getting in this case, after the pooling, we are getting only 2-dimensional feature matrices, right? Feature maps. but the classifier module reads it in as one-dimensional. So there is one function is there, flattening. So it will flatten, or it will convert the feature maps of 2D to 1D, right? And then the classifier layer reads the 1D feature vector and applies some hidden layers there, and ultimately classifies the output, or tells that this is this image, or this image belongs to this class. Okay. So till now, any confusion or any query? So this is the basic of the convolutional neural networks.
Sir, hello.
Yeah.
Could you please explain the last flattening part?
Yeah, flattening. As we studied that the pooling, or in case of convolutional neural networks, we are dealing with 2D matrices. Means we are dealing with the matrices. Those are 2-dimensionals, right? Because the images are arrays of pixels. Okay. But in case of this classifier module, the classifier modules is reading as a it is simply a ANN, right? Artificial neural network on multi-layer perceptron. Okay, so the input should have one dimension only. Okay, so for making the 2-dimensional feature maps to 1-dimensional, one function is there, that is flattening. It will just convert the 2D feature map into 1D. That's all. Okay. Sequentially, it will do it. Right? No other operation is there. It will just take each individual, and it will put in a vector. Okay, and that vector will be input to this classifier module. Okay, and after that you can apply a number of hidden layers, and finally you will get the output. One important thing that I haven't told earlier, that is the activation functions. Okay, activation functions that in this case the neurons doesn't really know how to bound the value. That means when to decide that this is the feature, or this is a particular pattern. For that the neuron should be activated. The neuron doesn't know for itself. For that case, activation function is required. The activation function tells the neuron, yeah, that this particular value, if you are encountering, then you will activate yourself in the next feature map, or you can suppress yourself. Right. So this is the main thing of activation function. It can be a linear or non-linear transformation, both, based on the inputs. Okay, there are several activation functions that are used in machine learning and deep learning techniques like sigmoid, tanh, ReLU, leaky ReLU, softmax, right? But among these, ReLU and softmax function are prime importance for the CNNs. In CNN, we use ReLU activation function. Right? It is a nonlinear activation function. In most of the deep learning models, we use ReLU, and some advanced version of ReLUs are also the leaky ReLU, like that. So what it will do, whenever it is encountering any value of a neuron, so it will check whether it is having a value greater than 0 or not. So if the value is less than 0, then it will make it 0. Like negative values, it will suppress the negative values and make them 0. And if the value is having positive value, then it will keep it as it is. Okay, that means, so suppose if xi is greater than 0, the output will be xi, or xi is less than 0, this will be greater than or equal to, so it will become 0, the output becomes 0. Right? That means for negative values, it is telling the neuron that don't fire. But if you are having some positive value or 0 or positive value, you will fire or you will activate, so that determining the patterns, that is positive values are having the important patterns in the image. Like as I said, the activation function activates the neurons, but the ReLU doesn't activate all the neurons at the same time, right? It suppressing some neurons to 0, or and activating some neurons to its particular value, and also it increases the training speed of the network. Okay. Now there is one activation function is there, that is softmax activation function. It is mainly used in the classifier module. Right. What it is doing, it is just representing the vector values of the output into a probability value of total output class. Right. That means it is just representing the probability distribution of the output classes. Okay. So this is the formula here, that suppose it is having that y values here, okay, and it is representing it through this formula. Okay, so this is the example. Suppose whenever we are processing the images through CNNs, right, or ANN, we are ultimately getting this type of value. Suppose there were 4 classes in that problem, and the output y we received like this one. Okay, this is the actual case that we receive in this form. Okay, so this form is represented to a probability distribution, right, like this one. So the maximum value is represented here, right? So ultimately it was the maximum here also. Yeah. So usko 0 to 1 के range में उसको represent करते हैं. So this is the case for softmax activation function. Now there is a term that is hyperparameters, but the parameter term is mainly used for the weights or the kernels of the neural networks or CNNs. Okay, the ultimate motto of any CNN while learning the patterns, it optimizes the parameters or the hyperparameters so that the model represent the images well. Okay, whenever we give them a new image, that it will identify it to its original class or to predict correctly. Okay, so in CNN or ANN, we are having iterations of training. Okay, different iteration or different epochs. We say that the model is trained in different epochs, different iterations. So after each iteration, the images are the model parameters are optimized, right, based on the output we are getting, based on the accuracy values or based on the loss values we are getting. Okay, so the hyperparameters are the variables that determines the structure of the neural networks. Okay, so there are different type of hyperparameters, and we need to tune the hyperparameters before training the networks, right? The first one is the learning rate. The learning rate in layman language defines how quickly the network updates its weights or the that network parameters or the kernel values, right? So how quickly it updates the network weights. So this is mainly determined by the optimization function we are using. Okay, generally, but we can manually define the learning rate on our own. Okay, so if you define a slow learning rate, that is a lower learning rate, the learning process will be slow, but it will ultimately converge smoothly, right? But if we use a larger, the training speed will be increased, but that convergence will not be smooth. Okay, it will oscillate a little bit. Then there is one term that is momentum. Whenever we are optimizing the weights, so optimizing the weights, so the that network parameters are optimized, like suppose this point is the optimization. So suppose for particular weight configuration, it is here, and for some other particular weight configuration, it will go there. So ultimately, we have to put it here. So this type of oscillation will happen in different iterations. So this direction is determined by this momentum. Okay. So so that the oscillation is prevented. Whenever we are in this position, the momentum will tell, yeah, you have to go downwards. Whenever you are in this position, it will say you have to go in this direction, like that. Okay. Then there is number of epochs. That is the number of iterations. That is this iteration, and the number of iteration we have to define. The user have to define it, and obviously the batch size. The CNNs mainly learns the images in a mini batch configuration. That is, while training the network with the images, at a time it will take some number of images, like suppose 32, and it will learn the features from that 32 images, and it will predict the classes, right? And again, based on the learned features of that 32 images, it will calculate the loss, right? And if the loss is larger, it will try to optimize, or it will try to reduce the loss, and again it will try to optimize the weights. So ultimately it updates the weights in the next batch. Like this, the learning of the patterns are happening, and optimization of the weights are happening in the CNN or any neural network. Okay. So this was all for the theory class.